Hi everyone, I'm Huanchen Lin from the University of Hong Kong. I'm here to present our work, Isotropic ARAP energy using Cauchy-Green invariants, which is cooperated with Freud M. Chitalu and Taku Komura. I will now motivate the problem that we are trying to solve. As we know, elastic objects in physical simulation have nonlinear deformation behaviors. And these nonlinear behaviors are represented by the notion of deformed configuration and the reference configuration that the objects naturally have. There's a mapping between the undeformed and the deformed configuration, but this mapping is generally nonlinear, so we don't know how to describe the mapping from any points in the rest configuration to the corresponding points in the deformed configuration. And because it is very difficult to describe such nonlinear mapping, we have to make an approximation. One possible approximation is the affine map. We will basically assume that given one particular material point or region around the material that is small enough, we assume that the mapping of the small region from the rest configuration to its deformed configuration is linear. The linear mapping is the affine map we show here. In particular, we are interested in the change of shape due to the affine map, and we don't care about the translation. This gives us the definition of the deformation gradient f. One particular type of deformation we are interested in is the isotropic deformation. Isotropic deformation means if you compress the isotropic solids down, they bulge out exactly the same amount in all directions. And if you stretch them out, they resist the same amount, no matter which direction you are pulling in. To measure how deformed the isotropic deformation is, one way is to use the deformation gradient to define a score for it. This score is usually called the elastic potential. Several isotropic elastic potential energies exist. Each such energy differs based on the type of elastic deformation it measures. For example, nuclear energy is analogous to a zero rest length spring, while the neo-Hookean model behavior is similar to the classic Hookean spring, with an implied rest length corresponding to the constant 3. The isotropic elastic potential energy is best described using these Cauchy-Green invariants. The reasons why Cauchy-Green invariants are so desirable are that, first, the analytic equations for energy, stress, and Hessian become significantly easier to implement and evaluate for time integration. Second to that, Cauchy-Green invariants make it easy to implement different energy functions in a single framework, as we can simply use mix and match to implement different energies, and the derivatives of these three invariants with respect to deformation gradient are known. The only things changing are those in the square boxes. Here are some examples. Rectly and neo-Hookean energy. They can be easily expressed in terms of the Cauchy-Green invariants. To obtain their gradient, we can simply plug the derivative of the energy with respect to Cauchy-Green invariants in the square boxes. And that's it. Similar things can be done to obtain the Hessian. Here's another example. STVK stretch energy. It's still very simple. We are interested in one energy called ARAP. ARAP energy has been very popular in many graphics applications, including shape editing, surface parameterization, and shape interpolation. We can try to rewrite ARAP in terms of the Cauchy-Green invariants, just like what we have done on Rectly, neo-Hookean, and STVK. However, something strange happened on ARAP. How to rewrite this term? This trace term does not correspond to any of the Cauchy-Green invariants, so this certainly stops us from expressing the ARAP energy using the Cauchy-Green invariants. And it also stops us from obtaining a gradient in a similar way. Now, I'm going to talk about some related work to address this problem. Smith et al. Introduced a new set of invariants based on the singular values of the deformation gradient, which require numerical singular value decomposition or polar decomposition. Another work, Wang et al., instead, used a tensor formulation to calculate the Hessian using the side-vector equation, but it also requires numerical SVD or PD. There are also some other works that involve computing rotation from the deformation gradient in some forms, but all of these methods depend on numerically factored rotation. Now I'm going to give you an overview of my presentation and our contributions. First, we give an isotropic ARAP energy using Cauchy-Green invariants. Second, we give a closed form solution for the rotation term of the deformation gradient. And last, we give a closed form solution for the singular values of the deformation gradient. Now, I'm going to describe the details of how we rewrite ARAP in terms of the Cauchy-Green invariants using an implicit formulation. To understand why we can't rewrite ARAP using Cauchy-Green invariants, we first use SVD to factorize the deformation gradient to understand what those invariants are doing in terms of the singular values. And also apply SVD to the problematic trace term. The problem now becomes very clear. We are trying to use some nonlinear invariants to rewrite a linear trace term, which is previously thought impossible. But how can we overcome this problem to rewrite the ARAP? Let's take a look at the trace term. One way to try to rewrite this term is to square both sides of the equation. The first invariant immediately pops up, but the terms on the right-hand side still cannot be expressed using the Cauchy-Green invariants. What if we repeat the same process by squaring both sides? Now, we successfully get an equation purely in terms of the Cauchy-Green invariants. After moving those terms a bit, we have an implicit expression of ARAP in terms of the Cauchy-Green invariants now. The trace term becomes one root of the Cauchy equation in terms of the three invariants. One way to analytically solve the Cauchy polynomial is the famous Ferrari solution. Now, here comes another issue. What if the element flipped? If we push too much on an element that it flipped to the opposite side, will the trace term still satisfy the Cauchy equation? Unfortunately, the answer is no. We will need to use another Cauchy equation for the flipped elements, but we can simplify it into one equation using J, the determinant of the deformation gradient. And finally, we can now define our implicit ARAP energy. The trace term is one root of the polynomial. Besides the ARAP energy itself, in many graphics applications, we are also interested in its gradient and Hessian. To do so, the first thing we should do is to calculate the partial derivative of the polynomial root with respect to the Cauchy-Green invariance. By noting the polynomial is always equal to 0, regardless of the values of Cauchy-Green invariance, we can take the partial derivative of both sides of the equation with respect to this invariance, and solve it by rearranging the terms to get the analytic solutions. Now we have the derivatives. F in the expression is one root of the polynomial. Also, a similar process can be done to calculate the Hessian. Since we have the derivatives of the trace term, the next step will be to calculate the gradient of the ARAP energy, which is as known as the stress tensor. We call the stress tensor formulation. The terms in the square boxes now can be easily calculated. To compute the gradient of ARAP, we can now do the same thing on ARAP as we have done on Dirichlet, Nilhokin, and STVK energy. It becomes very simple now. Next, I'll talk about how this implicit formulation also gives an analytic rotation formulation. By calculus definition, the rotation matrix can be given by taking the derivative of the trace term with respect to f. As we just discussed before, the trace term can be expressed as the root of the polynomial, and the derivatives of the root can be evaluated analytically. As a result, we have a closed analytic form of rotation matrix in terms of the deformation gradient, which is previously obtained through SVD or polar decomposition. But we don't need them anymore. And beyond physical simulation, analytic rotation is also useful for many other applications. Now, I'll talk about an alternative method to obtain the singular values of the deformation gradient in an elegant way. Recall the Cauchy equation. There are 4 roots in total, and they can be expressed in terms of the singular values. Since the 4 roots can be given analytically by Ferrari solution, the singular values of the deformation gradient can also be given analytically by a combination of the roots. Now, I will show the results of our implicit ARAP. First of all, since ARAP energy does not preserve volume, we add an extra volume preservation term. Mu and lambda here are Lemay constants. Here we show the dynamic simulation by compressing and pulling a bunny. To show the robustness of our method, we perform a scramble test by randomly placing the vertices in the space and then recovering it. Our energy can also be used to simulate cold-dimensional objects like cloth. As well as one-dimensional strand elements. Our energy can also be used in many geometry applications. Here, we show we can use the energy on shape interpolation and surface parametrization. The hand on the left and on the right are the input geometry objects. The 3 objects in the middle are the interpolation results. And next, we use our ARAP formulation to apply surface parametrization on the hand surface. Now, we are showing we use a single framework to simulate 3 kinds of energy. From left to right, the energies are stable near-Hookean, our ARAP, and STVK stretch respectively. All of these energies can be written using Cauchy-Green invariants. Using our analytic expression without any use of SVD or PD, our speedup is in the range of 1.7 to 4.6 when compared to existing methods. And finally, I will summarize our work. First, we give an isotropic ARAP energy using Cauchy-Green invariants. Second, we give a closed form solution for the rotation term of the deformation gradient. And last, we give a closed form solution for the singular values of the deformation gradient. Also, our energy formulation can be applied to a variety of problem domains, including cloth, volumetric simulation, mesh parametrization, shape interpolation, and so on. Thank you for attending.